This is your second video for Chapter 3. We're talking about interpreting scatterplots and starting to talk about correlation. Our essential question for the day, what does correlation tell us about a set of data? So, here are today's standards. We're going to be analyzing scatterplots, and we're talking about correlation and linearity. We'll eventually get to a least squares regression line with residual plots, outliers, and influential points, but today we are just going to talk about correlation in terms of bivariate data. That's your response variable and your other variable, your explanatory variable. Here, when we're talking about interpreting our scatter plot, okay, first we already know how to make our scatter plot and calculate it. We can also do it by hand. But when we're interpreting it, we say that there is a positive relationship whenever our scatter plot has a trend that's up, progresses up as you travel from left to right, or it's negative if progressively your points are traveling down when you travel from left to right. The form that it takes, linear, is what we're going to be concentrating on in the not so distant future, but it could be a curved possibility. There's also looking for possible clusters. We could have some situations that we have names for that I will give you in a little bit. Strength, how close do those points follow a form? So if it closely appears to travel in a direction like a line, then it would be strong. If it's got a wider band, then perhaps it will be more weak or moderate. Outliers, are there any deviations from the overall pattern? There could be a great scatter plot that you have that appears to follow a linear pattern. However, there are a couple of exceptions to that rule. Well, those would be what we consider to be our outliers, the deviations from that pattern. So let's look at some examples. Here we've got 6 graphs, and these are all scatter plots. Let's talk about the strength and the shape that it takes on. For A, we have a strong positive linear relationship. Clearly it looks like a line. That's a very strong. You will probably not run into a circumstance that is that straight unless you constructed it without using real-world data. B, I see we have a moderate positive linear relationship. This could be getting close to the weak end. My band is not very clear. C is a weak relationship. We can't really see a pattern in those data. D is a strong negative linear relationship. This is strong. It doesn't have to follow a straight line in order for it to be considered strong. It's very close to a linear pattern here, so it would be considered strong. E would be a moderate negative linear relationship. And F, it's pretty strong, but it's a circular relationship. It's very circular in shape. However, it's probably not likely that you will see something that looks like that. Okay, when we're talking about correlation, we are measuring the strength of the linear relationship. We're not talking about strength of a relationship that is curved. So our correlation coefficient R is what we're talking about here. R. This is the ugly R formula that's on your AP Stat formula sheet. It's not very useful. However, what we're going to do is we're going to calculate R in our calculator. This is, if you wanted to by hand, this is how you would calculate your R using your AP Statistics formula. What we should note about R is that when R is positive, it's a positive association, and when R is negative, there's a negative association. R only describes linear relationships. Notice, as we said before, this only measures the strength and direction of a linear relationship. So R will only apply when we're talking about a linear mapping. R does not change if you change the units of your X and your Y. So if you convert from minutes to seconds or so on and so forth, since you're working with two quantitative variables, even if you change the units, it does not change R. The relationship does not change. It makes no distinction between the explanatory and the response variables. Notice in your formula the commutative property of addition. I see that if I calculate my part for X's here and my part for Y's here, it doesn't matter which one is your X and which one is your Y in terms of R. In the end, X still needs to be your explanatory variable and Y needs to still be your response variable. But in terms of R, there is no difference if you were to switch your X and your Y data. R exists between -1 and 1. If R is 1 or -1, that is a perfect relationship. So it would be perfectly linear if it were an R equals 1 positive, and it would be perfectly linear traveling in the negative direction if it were a -1. Okay, so let's talk about looking at these scatter plots. This one, since it travels down as you travel from left to right, I see a clear band of data. There's a line that can pass through the center of that and gets really close to them. We're calling this a strong negative correlation. Here, I see a clear band that is traveling in the positive direction. So this is a strong positive correlation. I see a band traveling in the positive direction here. However, it's spread out a little bit more. My data is spread out. So this is what we call moderate positive correlation. And my data is spread out here in the negative direction. So this is what we call a moderate negative correlation. Finally, I get to my last example. This has no correlation. This data is all over the place, and there is really no relationship that we can tell. It is possible in a situation like this, if we collected more data, we would be able to observe a relationship. However, what we are given at this moment, we cannot find one. So here's the example that you have to work with. How well does the number of beers a student drinks predict his or her blood alcohol content? Well, 16 volunteers at Ohio State University drank a randomly assigned number of cans of beer. 30 minutes later, a police officer examined their blood alcohol content. Lovely example. So what we're going to do is we're seeing the number of beers, how it explains a blood alcohol content. So our number of beers is our explanatory variable, or our X's, and our blood alcohol content numbers, those are our response variables. We're going to put the number of beers as our list 1 and the BACs as our list 2, and construct a scatter plot with that information. And when we do so, we find this. Now I see that this has a clear band and a linearity to it. So this is a strong positive linear relationship that is created in this situation. Now to calculate the correlation, what we're going to do is from those data that have been entered into our list 1 and list 2, we're going to hit our stat button, arrow to the right to calculate, and arrow down so that we select ln reg a plus bx. I think it's selection number 8. And we're going to use list 1 as our x values, list 2 as our y values, and that will give us what R is. And our R is 0.894. See, it's close to 1. It's pretty close to 1. So we have a very strong positive correlation here. calculate the correlation again. However, so when you go into your linreg a plus bx, instead of list 1 being your x variable, let list 2 be your x variable, and then list 1 be your y variable, and see what it produces in terms of your correlation coefficient, your R. Well, it gives you the same thing. As we noted earlier, switching your values does not have any effect on R. It will have an effect on your graph and the relationship. So do not switch them in terms of determining your scatter plot and whatnot. However, switching them does not change what your R is. And that does it for today. Make sure you bring your book to class tomorrow, and we will see you.